Okay, recording in progress. All right. So when we get started, hide the meeting controls. Let me do that. Okay. So good morning and happy Friday. Today is the last day of March. It's hard to believe March is done. Tax time is coming soon. But that being the case, today we're going to do a couple things. We're going to begin with a continuation of sorts from what we talked about in the lab session on Wednesday concerning servers and server process architecture to kind of complete that story. And that was a last minute addition from this morning that I thought would be really important to go over to kind of round out your understanding of considerations about the machines with which you interact. And then we're going to pivot to a Jupyter Notebook, and we're going to look at some of the APIs for sampling from the discrete distributions that we talked about, the Bernoulli, the binomial, the geometric, the negative binomial, and the Poisson. And that's in support of project number 5, which is much easier than all the other projects. I'll give you a bit of a break, where you're comparing the population mean and variance to what you would calculate from samples. And so I have a Jupyter Notebook here to show you some of the scikit, the SciPy, I should say, SciPy APIs, which implements a lot of statistics routines. And so you're not going to be implementing these distributions. That's, I think, a little bit of a waste of your time. It's not the purpose of this class, but certainly being conversant with some of these distributions and their implementation in SciPy is very important. And then with the balance of that, as time permits, we will continue on with our continuous distributions, continuing off with the exponential distribution, which travels in time. Kind of jar your memory on that, and then proceed with the gamma distribution, then the normal distribution, which is very, very important, the standard normal distribution, which is the basis of outlier detection, so-called hypothesis testing. And then we'll look at the central limit theorem, which is probably the most important concept from a standard undergrad probability course. Okay. Any questions? No? All right. But before, oh, yeah, I've sort of come to autopilot with some of the things I talk about in class. Okay. So where we last left off, one of the things we talked about was the so-called von Neumann or Princeton architecture. And it goes back pretty far, and it talks about the structure of the components of a modern computer. And this is still how modern computers are organized today. And it'll change dramatically when quantum computing becomes a reality. But nonetheless, I mean, rather, until then, we're kind of, we have, I won't say stuck with, but we have the von Neumann or the so-called Princeton architecture. And we said it's fashioned after an organism. You have a high-speed communication substrate, and each of the components, both those components, the I/O devices that get data onto your system and push data off of your system, as well as the microprocessor, which houses the CPU, which is responsible for executing statements, whether those statements are calculations or those statements involve setting up a transaction for the exchange of data between components on your system. Any questions about that? No? Jar your memory? So when we have a program in execution, that's called a process, and a process needs pieces of information reflecting all of those interactions that it has with the various components for your machine, for your von Neumann architecture. And when you are running programs on your system, it appears to you that these programs in the executable form processes have sole access to all of the parts of your computer, but that's not the case. Underneath the covers, your operating system is giving each program running on your system, some you see, some you don't see, is giving each program on your system a little bit of time on your processor. And so when it does that, it needs to write down pieces of information corresponding to the usage and the data that your program owns on each one of these parts of your computer. And so when it's time for that program to give up the system for the next, to make way for the next program to have some unit of time over which to execute, the operating system writes down all of that current state scattered around the components of your von Neumann machine to the so-called process control block, which is a special data structure representing the running state of your program. And so then it switches to the next program by selecting its process control block, that big data structure, and then it loads all of the parts of your von Neumann machine with the current state where it left off, and it resumes running. And so you believe that your system or your program has sole use of these finite resources on your von Neumann machine, but in reality, it's sharing it among the many processes, dozens of them that are running on your system. Okay, to jar your memory. Any questions? No? So when we extend this, there are many applications that you're using now, like Zoom, we're using to record this, as well as cloud storage. Your program consists of a number of pieces. So if we take, for example, email, I know email is so, going obsolete. Let's say Slack or Discord. There we go, Discord. You have parts of your software that runs on your machine and other parts of your software that runs on another machine. And these components, yes, absolutely, they're processes, but your quote unquote application consists of a bunch of processes, some of which might be running on your computer, some of which might be running on other computers scattered around your network. It could be locally here on campus or anywhere around the world on the larger internet. And so these so-called network applications are immensely useful. And the whole goal of a computer networking class, if you ever have opportunity to take one, it's a standard computer science course. It's the study of all the engineering artifacts involved in processes that exchange messages. And then at a graduate level, something called distributed computing are all the concerns for how you get these distributed processes to coordinate with one another in order to give the illusion of a single application. So for example, when I book some travel and I'm going to go to a new area, be that driving or a flight, I like to do a Google Street View virtual drive. And for me, I go to Street View and Google Street View, and then I click on the interface. And on my browser, I'm driving around, but that involves several servers that aren't on my machine. And what this architecture, this so-called network or distributed application allows you to do is it allows you to consolidate resources, but also allows you to make use of very powerful processors, von Neumann machines, without necessarily having to lug around a big desktop size workstation. And so these network applications are very, very popular. And as advances both in network speed as well as computation speed increase, they're only going to get better and better and better, including wireless communications. Okay, and so when you create network applications, you write programs that run on different systems. And the schematic here on the right-hand half of the screen represents a so-called computer network. And I won't go over all of the components, but I'll just point out some differences among parts of a typical internet architecture. You have these so-called networks, like this network here. That network is the cell phone wireless network. Didn't expect that to happen. Let's try that again, because I'm using the mouse to draw because I forgot my sketch pen. This wireless network is nothing more, almost like a big Wi-Fi access point, but they're located at the cell tower, and underneath the covers, they use different technologies because they need to throw electromagnetic energy over longer distances. Now, a network is just a set of interconnected systems, so-called hosts or end systems, and these end systems, when they are directly connected, they're called a single network. Now you have other components here. You'll see these things that look like hockey pucks with these X's. Those are router devices. And it's the job of these router devices, or so-called packet switches, to take your data and to examine where you want it to go and make a decision as to where it's going to forward that data. It's a so-called store and forward device. And it's the collection of these routers storing and forwarding chunks of data or packets in which you traffic that results in your ability to send data from, say, your cell phone on the mobile network, ultimately to a server here on Canvas. This is going to be interesting. On Canvas at Clark University. Let's see if I can circle that. Okay. Does that make sense? And so we're not going to talk about the communications issues. I would highly recommend you take a computer networking course, a whole semester on it, to learn more about those details. But what we will talk about is the programmatic consideration. And so when you look at network technologies, often they talk about the so-called network stack. And just like in Python, you have a series of APIs. You have the pandas APIs, you have the matplotlib APIs. You have various APIs that serve various purposes as it pertains to exchanging data between processes on different machines scattered around the internet. And so the so-called application layer is that programmatic interface that you have access to. You don't have access to the others, but in a traditional networking course, you need to understand what these APIs do, because that ultimately impacts your ability to create these network applications. And so when you design a network application, oftentimes you typically would study as part of that the so-called server process architecture, how you arrange these processes and the considerations for that arrangement of processes scattered around the network. And there are two possible structures that this arrangement of your processes can take. One is so-called client server, which most people use, and the other is called peer-to-peer or P2P. Have you ever used something like BitTorrent or some of these music sharing platforms? I know you don't do that anymore, right? It's all streaming. Have you ever used BitTorrent? No? Little, okay. No, I'll kind of spend a little bit more time on peer-to-peer when we get to that section. And so, all right. So the so-called process architecture falls into two major categories: client server and peer-to-peer. And it's the set of considerations about how you scatter your processes around and what the nature is for their interaction in order to implement these so-called network applications. And so let's look at the client server architecture. Now, in the client server architecture, you have two processes, and these processes are given names. One's called the client process, and one's called the server process. Now, a server process is not a machine. It is the actual process, the program in its executable state. Oftentimes in practice, people will refer to the hardware, an instance of the von Neumann machine, as the quote unquote server. And the reason for that historically is in highly specialized applications, an entire von Neumann machine will be devoted just to that single process, that server process. And examples of that include things like Google Street View or maybe Amazon's shopping website. You have so many requests or so many messages coming into it that you devote the entire machine, von Neumann machine, to that single purpose, running that process that accepts incoming messages, checks databases for information, and then responds to it. Does that make sense? And so a process is the server. The server rather is a process in this so-called client server architecture. Now, there are some requirements for these processes, and sometimes it's described online and in the literature as the so-called server role and the client role. These are things that in order to implement a client server architecture or organization of your communicating processes, they must satisfy these requirements. And so a server is always on. It's always running, it's always available, and it has a permanent address that allows other processes around the internet to reach out and contact it and send it messages. Now, these messages are typically requests for some type of information. When you open up your browser and you type, for example, www.cnn.com or www or canvas.clarku.edu, Your browser is a process on your machine, and that clarku.edu is a process on a server for a data center managed by Clark University. Now, I'm not sure if Canvas sits on Canvas's data center or if Canvas for Clark sits in Clark's data center. I'm not sure where it is, but there is absolutely some process, some server that when it gets the request from your browser, it's looking at its file system, its database, for an HTML file or PHP file. It brings it into memory, sends it back to your browser. When your browser gets it, it renders or draws all of the primitive specified in the user interface for that PHP file. So all your web server is just some process that is always on, and its IP address, or rather its address, has to be permanent. It can't change because you need to be able to contact it by that name. The other requirement is that when you have a server that gives out data, that data has to come from somewhere. Now, it's not an absolute requirement, I misspoke, but oftentimes for high capacity servers, processes, you often have data centers, which is an aggregation of a lot of von Neumann machines with very high speed and high density storage. Does that make sense? Any questions? Okay. So a client role or client is a process that communicates with a server. And the client is always the process that initiates the conversation. So you run your browser, process runs on your machine, you type in this URL, Uniform Resource Locator, www.clarku.edu, then your browser process takes the address associated with that, and we won't talk about how that address is obtained from that name, and then it goes ahead and sends a request, please get me this web page, and that request is received by Clark's web server process. It looks up in its database the correct HTML file, sends it back to your browser, and your browser draws that as the main page of clarku.edu. Okay, does that make sense? Okay. Now, because the client process on your machine initiates the conversation, your client process can be what's called occasionally connected. It doesn't have to be always running in the background. You can turn off your machine and then turn it on an hour from now, type in www.clarku.edu. It initiates this request, but the server process in the data center for Clark, that always has to be on and it can't move. Okay. Does that make sense? Any questions? No? All right. So that's the client server architecture. Let's look at the peer-to-peer architecture. Peer-to-peer architecture is kind of this hybrid. You have your server process, and it doesn't have to be always on. But the peer-to-peer architecture is a little bit different, and we'll talk about that in the next slide. But peer-to-peer networks have this property of so-called self-scaling. Now, the reason for this self-scalability is that when you join a network, you need a resource, right? You decide you're going to join the internet by turning on your laptop, connecting to the wireless network, and you want information from clarku.edu. Maybe you want the latest news that's on the main page for the university. And so you have an information need or a need for some resource, and that resource is available on the server. Now, with a peer-to-peer, rather with client server, when you join the network, you just join in order to get something from the servers that are reachable on the internet. But with peer-to-peer, not only do you use something or need something that's available from some server on the network, you also have to bring a resource to the network to make available for others. And so BitTorrent, that I alluded to before, it's a type of peer-to-peer network, and it's used for downloading files very, very quickly. And what BitTorrent says is if you want to participate in this network, you might be able to request files, but you also have to make files available for others. And so what ends up happening if you have 1,000 people or 10,000 or 1,000,000 people that join this BitTorrent network, you have 1,000 people or 1,000,000 people who also bring or make available these files for others to download. And so the reason why BitTorrent makes file download faster is because instead of downloading a whole file, you're downloading pieces of files from many, many places, and that makes it much, much faster. Does that make sense? Okay. And so a peer is nothing more than a process, but this process implements the client role. It can initiate requests, but it also implements the server role. It can respond to requests and deliver resources to those that want it. Does that make sense? So let's go next slide, and hopefully this doesn't go horrifically wrong. Let's define peer number one. We'll do red this time. And I'll just draw a circle representing the first peer. And then let's define peer number two, P2. And let's also draw this as a big circle. I'm using the mouse instead of my sketch pen. I brought the pad, but I did not bring the pen, which kind of makes it useless. Okay. I wonder if this pen works. No, that's the pen. I don't have the pad out now. I unplugged it. So we have, let's for the sake of discussion, let's draw a disk, and let's imagine that disk has some music there. So let's just say file one, and let's imagine also peer two, it has storage, has a database, and let's say that has some music on it, music file, and let's say that's file two. Okay. Now, as a client, I'm going to say that client role, it initiates requests. I'm going to draw a little port here, a little plug, and I'm going to label that with a C for client. And I'm going to label the server role, it's always on, it responds to requests. I'm going to label that with this port S. Now, if client server, the client, we said, it initiates the request. And let's say it says, get me some piece of music, right? And so what does peer two do? Okay, it's server role. It unpacks that get request. It looks up the file in its file system. It retrieves the file, puts it in memory. So here's file, I'll just say F2 because it's more brief. And then the server does that work of retrieving the file, and then it sends it back across the network in a response, file F2, back to peer number one. That's the client-server interaction. Now, to be a peer, you have to both implement the client role as well as the server role. And so peer one, okay, if you want to participate, you're not just going to be getting files from other people. You have to make your files available. So peer one implements a server role, and peer two implements the client role. So now peer two, through its client role, it can make a request, get, G-E-T. It's hard to do this with the mouse. And when the server role on peer one gets that, it does some work. What is the work that it does? Okay, it retrieves file one, if that's what the request is. It takes file one, brings it into memory, F1, and then it sends it back across the network to peer two, and that would be file F1. And so a peer is nothing more than a process, a program in execution that runs on a machine, and it can run on the same machine or on different machines scattered around the internet, and they implement both the client role and the server role. But a peer, it doesn't have to be always on. It can be occasionally connected. You can turn off your machine, and what that means is that your peer is not available for others on the network to implement. But if you have 100,000 peers running across the internet, peer three through peer 100,000, right? If your peer drops out, that's fine. you still have 99,999 other peers that you can interact with. Does that make sense? Any questions? Okay. So that's a peer-to-peer process architecture. Now, when we look at servers, you might wonder, well, what actually is a server? Well, when you deal with the server hardware, the von Neumann machine, they typically come in a high density format. And that's an example here on the left. It kind of looks like a pizza box, right? For like a medium or large size pizza. And so you take this and you put it in what's called a server enclosure. And that's an example of a server enclosure on the right. And it kind of looks like a wardrobe, those wood wardrobes standalone that you can buy at the furniture store. Um, and so if we look at it, this server enclosure, it has some slots that are marked. And each one of these slots is a so-called 1 unit or 1U. 1 unit or 1U is 1.75 inches. And in server physical representations, they've standardized on the size of things. So if you go off to like CDW or ThinkMate Computers or Dell or whatever, and you bought a server form factor for your von Neumann machine, it's going to tell you how big it is. This is a 1U server. This is a 2U server. And it just refers to the physical size, because if you go to this enclosure, this armoire looking thing, it's typically metal, and it has these slots and these rails that you screw your server hardware into, and it is on rollers, and you can literally roll it out or roll it in like a drawer for like a chest of drawers or a dresser. And the reason for that is because if you have many thousands of these things in a data center, a collection of these servers, and you're going to maintain them, you want to make it easy to access them and do whatever maintenance you might need to as part of their regular operations. Does that make sense? Any questions? No? And so this 1U, a so-called full height enclosure, stores, has space for a total of 42U. And so that's the standard height. You can get heights for server enclosures that are smaller or larger, but the standard in terms of what's considered the regular size is 42U. And so this 42U, as the name implies, can fit 42 of these 1U server units, and a single server unit, von Neumann machine, can have as much as tens of terabytes of storage, and as much as these days you can get 64 processors in one of these 1U units. So you can imagine just how much computational power you can have in one of these 1U racks, and a 1U rack is about this tall and about 2 feet wide and about 1.5 feet, 2 feet deep, right? And typically they're on wheels, and you can roll them around and arrange them. And one of the designs behind these 1U servers and 2Us is that you'll notice these vents on the front. They suck air in through the front, and then they vent the hot air, cold air in the front, and they vent the hot air out the back. And you notice this enclosure, the front and the back of it are mesh, and there's usually an access door on the front. And so all of that hot air used to cool these processors as they're running, they heat up, it's wafting out the back of this enclosure. Okay. So when you design a data center, it kind of looks like a library. Like in a library, you have these stacks of books. In a data center, you have these full height 42U server enclosures, fully populated with servers, and you line them up to create rows like you'd have stacks in a library. And so when you collect these things together, as you can imagine, there's a lot of hot air wafting out the back of them, and a single server, 1U unit, can take up anywhere from 900 watts to just over 2,000 watts of power. So if you imagine 2,000 watts times 42 of these 1U units, that's just one server full height 42U rack. Imagine if you have 1,000 of these racks. That's a lot of heat, but it's also an unbelievable amount of power that they need. And so because of that, when you have data centers, you don't just have a data center as a building where you have a bunch of servers. Data centers are built specifically for the purpose of housing these servers. Does that make sense? Any questions? No? And so typically, if you go to a data center, it has what's called a raised floor, and it's a bunch of metal frames. And these frames implement a sort of checkered pattern. And you have these rectangular floor panels, almost like tiles, but these tiles are very rigid and they can support a really large amount of weight. One of these fully populated 42U racks can easily be about a couple 100 pounds, right? So you have to support a lot of weight. And what they end up doing, the reason for this raised floor, is that they have tremendous cooling systems and they pump all of this chilled air underneath the floor. And so there's a gap between your floor tiles and the subfloor, and there's all this cold air that goes circulating underneath the floor. Now, the reason for that is part of that special design for the building. Because you have all of that power being consumed and because you have all that heat being generated, you need some flexibility and specificity on where you channel all of this cold air. And so some of these floor tiles are regular floor tiles, but some of these floor tiles are grates. And when you have a grate instead of a floor tile, that cold air circulating underneath the raised floor has the opportunity to go up, right? Because the air wants to go from high pressure environment to a low pressure environment. Okay, does that make sense? All right. Any questions? Yes. Mm-hmm. Ah, ha, ha, ha. I'm glad you asked that. There has been, at least in my understanding, at least the earliest I've seen people talking about it, the last 10, maybe 15 years ago, so-called green high performance computing. And they often try to use alternative forms of energy in order to sustainably power these data centers. And so some use solar power, some use wind power, some kind of play the game, and I call it the game of buying carbon offsets, right? You're just paying for your uh, overuse of energy, to be honest with you. Some also try to locate their own power generation, right? And I'll get to that, I think, in the next slide, a little bit. Yes, okay. Um, so they do all sorts of things. Most modern data centers, they have their own power generation plants. And usually it's gas. I know some use hydrogen fuel cells, some build their own solar farms and things like that. And then there's another side of it where you have specialized von Neumann machines that are more energy efficient. And depending on the type of computation that you need, they don't put your computation on your process on a von Neumann machine that uses more energy. They put it on one that uses enough energy that you need. And so that's a really important question. In fact, in Holyoke, Massachusetts, there's the Massachusetts Green High Performance Computing Center. We're not a member of it. UMass Amherst is, and a bunch of other universities. They have both the design and the hardware to try to minimize energy usage. They have policies, and they also try, with an emphasis on try, to recruit more sustainable sources for energy. So it's kind of all of the above. As green energy further increases in terms of the percentage of the energy budget, it'll get better. But right now, natural gas is a big one that they use. Natural gas is better than coal, but it's still a fossil fuel and still has that negative impact. Did I answer your question? Okay. And so you'll notice that in the design of the data center, the cold air comes in the front, and that's afforded by this grate that allows the cold air to come up. It pulls these server instances, pulls the cold air through the front, and then it wafts it out the back. And so you end up with what are called cool channels in this area in front of the data center in front, for this stack, as it were. It's cold air, but if you were to walk behind the data center, walk behind these racks, but in this channel, this little hallway, it would be very warm. Now, warm air rises, and so the good news is, because that warm air rises, you can now put vents up top that suck in that cold air, send it through the chillers, and then wafts it back underneath the raised floor. And so the reason that data centers are designed, or are huge buildings, like almost like warehouses, they're specifically designed for the purpose of housing servers, is because you need a lot of specialized things in order to get this to work efficiently. Any questions? No? And here is another cutaway view. In this example, they have the cold channel or cold hallway between, and they have the hot channels in the back. Hot air rises, and you see that the hot air goes to these vents that recirculate it through the chiller. Okay. Any questions? No? Now, when they locate data centers, they don't just build them anywhere, right? They often build them to be conveniently located near power substations. And so if you're ever driving across the country over long distances, you'll see these big, impressive looking power lines. And these power lines typically carry much higher voltage and current. And then it's once it gets closer to areas where houses are, they electronically subdivide this power ultimately to form residential power that is then sent to houses either on power lines up above or buried power lines in more urbanized environments. And so this is a picture of one of Facebook's data centers. It's an architectural rendering. And they usually locate these things. I know Facebook built a bunch of data centers in the potato fields of Eastern Washington State. And so you'll usually find data centers in rural, large areas, and they like to conveniently locate them close to power substations because the power has less distance to travel. It's more abundant near the power substations, and they also use that as a backup along with or alongside their own power generation facilities. Moreover, to go back to your question about the environmental impact and carbon consumption and the green considerations, when you have a lot of this space, like potato fields of Eastern Washington, you can also very easily co-locate solar generation plants as well and wind farms. Okay, any questions? No? All right. And so all of this is to talk about your processes and they scale. And when you upload to OneDrive, there's a server instance, both the process and the von Neumann machine on which it runs, somewhere in Microsoft's data center, maybe in Eastern Washington, that is storing that information. And this is just what it looks like physically, as well as the considerations for the process architecture. And so these are some examples of what inside of a data center looks like. And again, you see these stacks, and these are actual data centers. And you see the cold channel and you see the hot channels. You'll know where the hot channel is. If you look up at the ceiling, you'll see the vents. And then if you turn the lights off, it looks really cool. Each one of these 1U units, they usually have some sort of visual indication of various things happening, like access to the network, as well as access to the disk. And the reason for that is when you see that something's broken, it's kind of nice to visually inspect it and have a sense of what's going wrong. But they don't just physically inspect things. They have lots of sensors instrumenting these server instances, these von Neumann machines. And if something is going wrong, typically they get an alert, because if you have thousands of these and hundreds of thousands of these, it's not practical to visually inspect every single one physically. Okay. Any questions? Does that make sense? All right. And so the goal for this course going forward in the future after this semester is to also have people set up with cloud accounts on which to run your Jupyter Notebook and your analyses, so you have access to a lot more computational power than what you'd have on your desktop or notebook or laptop. But we're just not there yet in terms of finding a solution that is scalable. Okay. Any questions? No? All right. So Processes are programs running on a host, and clients initiate a request, servers accept requests, perform work, and give back responses. And peer-to-peer are processes that implement both the client role and the server role. Now, when you implement client server or peer-to-peer applications, there's a set of APIs called a socket interface, and this allows you programmatically to write applications that can either send information or receive responses from servers. And so if you took a computer networking course, you learn all about the mechanisms, their designs, the considerations, and the interactions associated with enabling this writing of so-called network applications, be they client server or peer-to-peer. Okay, any questions about this? No? So if you're computer science, or even if you're data science, if you have it in your curriculum, I would highly encourage you to take a computer networking course. It's fun, but it's also a very nice skill set to have among your skills. All right, questions? No? All right. Okay, so let's end there. Whoa, time just went. All right, and let's go to the Jupyter Notebook, and we will, let me bring this down, keep, and let me bring up the notebook so I can get rid of that. And let me bring up the notebook. Hello, that is, what's that? No, that is where I left off, right? That's continuous distributions. So where's my notebook? It's right there. All right, so let me bring up screen share. And let me go to Safari. Let me maximize that. All right, oops, what is that? All right, there we go. All right, so let me hide meeting controls. And we're up. Okay, so I can also post this on the Moodle Canvas site. So in homework project number 5, it's a lot easier than the other projects. Thought I'd give you a little bit of a break, but it's really important, the concepts that are there. And so we certainly covered the matplotlib library. Matplotlib isn't the only way to do visualization. Seaborn is another library. The APIs are a little different, but the types of visualizations implemented in Seaborn, which I'll leave to you to look at yourself if you're interested, they're much more sophisticated, right? If time permits in the remaining weeks of the course, maybe we'll go over a little bit of it, but it's not part of the core consideration for the course. And so the other one is called SciPy. And SciPy is a scientific library that implements all sorts of very important concepts like optimization, like function approximation, as well as probabilistic concerns. And so we're going to import various modules from the SciPy statistics package. And this does all sorts of stuff. All the distributions, the probability mass function and the probability density functions for the continuous ones, they're all implemented, but it also allows you to sample from these distributions. When we talked about the relationship between populations and sampling, we said out there is floating around in the population some distribution, and that distribution, the so-called population distribution, is governing the values for the data that occurs. And so you don't have access to its governing parameters like the mean and the variance, but you can certainly estimate them by calculating the sample version of the mean and the sample version of the variance based on some sample that you obtain from the population. And so here, for project number 5, you're going to compare what the theoretical population values are to those sample values. And you'll see that as you increase the sample size, the ground truth population parameters and the empirical, as they're called, sample values are going to get closer and closer and closer to one another. And it's almost creepy in a way that it works. Why it works, people can prove it, but why does it happen? That's a philosophical question. Go ask someone in the philosophy department. But that being the case, in this example, or rather in project number 5, you get to see what the population parameters are, right? Why do you get to see them? because the only way to show you that it really works is for you to see them, right? But in reality, and that's what I want to stress, you don't get to see the population parameters. You don't know what the true population mean is for the homeless population in Worcester. You'll never know what it is. All you can do is sample. Maybe you find 100 homeless individuals and you ask them your age, you compute the sample mean. And so the purpose is for project number 5 is to show you that this really works and to show you that when you increase the sample size, instead of 100 members of the homeless population, maybe you contact 200, that sample quantity gets closer and closer and closer to the ground truth. Now, I really want to stress, that's why I'm saying it again, that in reality, you don't get to see the population parameters. But computationally, in order to demonstrate that this principle works, you get to see it. Does that make sense? Okay. So here from SciPy Stats, we're going to import the APIs, or rather the modules, for all of the discrete distributions that we talked about, the Bernoulli, the binomial, the geometric, negative binomial, and the Poisson. And just for good measure, just to show you what's there, SciPy Special can do permutations and combinations. There are also APIs where if you give it a set of objects, it'll actually show you what those collections are. Okay, so let's import these modules. Any questions? Let's import these modules. And this was just for giggles, computed permutation and combination. That's not really the focus of what I'd like to talk about. But we're going to set the number of samples to 500. And then here in this next cell, we have the Bernoulli distribution. And in the SciPy APIs, everyone made the engineering meeting. So all of the APIs are very consistent. Go figure. And so here, recall, and I'll give you this example, for the Bernoulli distribution, it had a governing parameter, P, which is the probability or rate associated with the true outcome, right? Again, Bernoulli, to jar your memory, it's a stochastic system. The observable quantity can take on one of two states. And in all of the theoretical discussion, they call it true, false, or 1 and 0. But it could be chocolate ice cream, vanilla ice cream, could be male, female. Any problem where you're trafficking in two-way outcome on independent trials where one of the outcomes is associated with one probability and the other is associated with 1 minus that first probability, that's well defined or well described by this Bernoulli distribution. And so here we set the Bernoulli p-value, and that's going to be our population parameter. Ground truth, we're imagining this Bernoulli distribution governing some quantity in the population has a success rate for the true outcome of 20%. Does that make sense? Okay. And so we know from the theory that the population mean, mu, is p, and the population variance, sigma squared, is q times p. Okay. So if we know what Bernoulli p is, 20%, we know that Bernoulli q is 1 minus 20%, which is 80%. We can actually calculate what the population mean is and what the population variance is. But again, you don't in reality get to see that. So we're imagining then, what if we sampled? So here, the standard is in the SciPy stats package is when you do sampling, you're calling this RVS, random variate sampling, right? And that's the standard on each one of these distributions. This is nice. And when you call RVS, random variate sampling, on the Bernoulli, you have to give it that parameter, P, and then you give it the number of samples. Does that make sense? Okay. Now, of course, when we talk about this idea of inference, what you're enterprising to do is find a reasonable replacement for that Bernoulli P that you don't have access to in the real world. Does that make sense? All right. So here we say, okay, I'm going to call it coin flips, and coin flip is going to be true if it's heads, false if it's tails. And I ask Bernoulli, RVS, given a success rate, heads of P, 20%, generate 500 many samples. So I go ahead and I do that. And now I'm going to take one of the coin flips and I can say, okay, Well, given one of these coin flips, tell me what the what the what the probability is associated with it. I can evaluate, and this is also standard in this package. I can evaluate the probability mass function, so I call Bernoulli PMF. I give it the value, true or false, in the case of the Bernoulli, and then I give it the parameter Bernoulli P. Okay, so it kind of makes sense. The probability of getting a zero is 1 minus the probability of getting a P, and it gives me zero point 0.8, which is 80%. Does that make sense? Okay. So now, when I did this sample, I said, give me 500 flips of a coin, and I can actually see that array of flips for those 500 many flips that I asked it for. And what you'll find is that if you counted the number of successes won in this array, it would get closer and closer to 0.2. If it's just 5 samples, it's not going to be that close. If it's more than 5 samples, at some point, it gets really, really close to the original 0.2. And so one of the tasks in Project 5 is to do two things. You're going to calculate the mean and the variance from what you know about the population. Then you're going to sample, and then you're going to evaluate the mass function, knowing what the ground truth parameters are. And then you're going to calculate all of that from your sample and show how close it gets as you increase the sample size. Does that make sense? Any questions? No? All right. So if we can sample from the Bernoulli, okay, we can also plot the histogram of those samples. And if I plot the histogram, one of the things you'll notice, there'll be a 20% to 80% proportion as you increase the sample size between the number of falses, the zeros, which is that left-hand bar, and the number of trues that count, which is the right-hand bar. Does that make sense? Yeah? All right. And you can just choose whatever population values you want, right? That's up to you on the project. All right. So now we did that. Let's look at the binomial distribution. We said the binomial distribution is a sequence of n many slots wide of Bernoulli trials. So that's like you flip a coin 10 times, or you take 10 coins and you flip them. It's the same problem. And what the binomial is asking is what's the probability of getting some number of heads given a rate of probability P and given a number of trials, n many wide. Does that make sense? All right. So again, okay, we set the n parameter for the binomial to 10. In this example, you can set it to whatever you want. We set the p variable or parameter, the success rate for a true. And now we call binomial RVS random sample. And we're going to use these population parameters, again, stressing that I'm giving it to you so you can verify it. But in reality, you don't get to see them in real life. And so let's recall that the mean of a Bernoulli distribution is n times p. And the population statistics, the mean and the variance, are typically some function of the parameters that you give it. So you can absolutely calculate what they should be and then compare them by calculating those same quantities from the samples that you get. And so here we have n is 10 and p is 0.2. And then we sample that 500 many samples given the population parameters of n slots and a success rate of p. So now if we do that, let's look at these 10 coin flips. So the first round, out of the 10 coin flips, we only had 1 true. Out of the 10 coin flips in the next round, we had 6 true out of the 10. In the next one, we had 3 true or heads out of the 10 flips. And so each one of these samples that we get is the number of successes out of that 10 many trials. Does that make sense? Okay. And so we also can plot a histogram, and we get a histogram, and along the horizontal axis, that's the number of successes. Along the vertical axis are the counts. Does that make sense? And so if you were to grab one of the samples, like that first one, which was, what was it? Was 1. So 1 true out of 10 flips, and you were to evaluate the mass function, that would give you the probability associated with having 1 heads out of 10 flips. And then you could take your array of samples and actually count how many of them were 1 and how many total did you have 500. And as you increase the sample size, it's going to get closer and closer and closer to the ground truth, where the ground truth says the mean is n times p and the variance is n times p times q. Does that make sense? Any questions? All right. And so I'm just going to, for the others, look at the sampling routines just to show you that this is very consistent. This was the binomial, plot the histogram. And this is a geometric. The geometric was a stylized sequence of true and false heads and tails. And the stylized sequence had all failures ending in a single success. So we set the p-value for 20% in this case for the geometric distribution, and then we do random variate sampling. Produce me some samples, 500 of them. So here it says 3 trials before success, 3 trials before success, 18 trials before success. And once again, you can calculate what the mean and the variance is for the population using the parameters, and we went over that in class on Monday. And then you can also compare that to what you get from the samples by calculation. And again, you'll find that as you increase the sample size, it gets closer and closer and closer to what that ground truth is that you've calculated. Does that make sense? All right. So this is really to convince you that, yeah, this stuff really does work. But really stressing, and stress it again, that in the real world, for example, you don't get to see geom p equals 0.2. You don't get to see that in the real world. You don't have access to it. And the only reason for showing it to you or having you choose it is to prove to you that what you calculate from the sample really does approximate well what you have floating around in the population that you don't have access to. All right, so that's the geometric sampling, and we'll call that interview rounds. And we can plot the histogram of that, what it looks like. And as you change the parameter, you'll see these histograms also change to suit. This is the negative binomial, which is just a sequence of geometrics. Again, we have the number of successes we want. We have the rate. And what negative binomial talks about is the number of trials in order to get that many successes. So if the probability of a success is really small, 0.2, you'll notice these numbers are pretty big. It takes you 29 trials and it took you 57 trials in order to get 10 successes with a small success rate. If we bumped up the success rate to 0.8, for example, and we tried this again, you notice that it takes fewer trials in order to get that many successes. Does that make sense? Okay. So let's set that back. That's a negative binomial. And then you can also plot what the negative binomial looks like. And then lastly, the Poisson talks about the arrivals, the number of arrivals for events in time in a standard unit of time delta t that has to be consistent. And we had the lambda because it's fancy. And here we said on average 3 events per unit time. And so we look at the number of arrivals that we sample being consistent, random variate sampling in this API. We give it the ground truth parameter, and then we tell it how many samples we want. And so here it said, all right, in the first delta t, we had 3 arrivals. The next delta t, 6 arrivals, 2 arrivals, and so forth. Okay. Any questions? Does that make sense? All right. And so the whole goal, again, is to demonstrate by measurement that the sample quantity, what you calculate from samples, gets really, really close to the population quantity as the sample size increases. All right. So we'll end with that. Any final questions about it? No? All right. Okay, so let me bring this down, and then we will probably just have a little bit of time. We have about 9 minutes, not that much time. All right, let's look at, I think it was 19, and we'll just see how far we can get, maybe not that far. And I'll set up the gamma and then see what a good stopping plate. I'm hungry, that's why I said that. What a good stopping place should be. All right, so that's up. What's on my screen isn't always what's up there. So, all right, so um, I've posted some other material about the continuous distributions as well as what are called moments in max likelihood, which we'll talk more about next week, project number 5. We're going to have it due Thursday night. I don't like to have things due Friday night, but if people need the extra day, I'll certainly oblige because I expect you to be normal people and enjoy your Friday night, right? So I'm not that type of person. So we're going to have it due Thursday night. It's a lot easier, give you a break than all the other projects. Probably the easiest project of the semester. Um, I will also post the Jupyter Notebook that I just showed on the Canvas side. After today, 4 weeks in one day. It's getting really fast. All right. So that being the case, where we last left off, we talked about the exponential distribution. And this exponential distribution talks about time, the so-called inter-arrival time, or the time that until which you see the next event occur. And so anytime you have a scenario that traffics in the time, it's always well described as an exponential distribution. Now, of course, time is not negative, right? And for the exponential distribution, it's only defined for time values that are greater than 0. Now, when we talked about continuous distributions or real value distributions, we made the analogy of peanut butter being spread on bread. And so in this case, we have our knife, and here's where my cartooning class that I took is trying to help me. And you have a standard unit, 1 unit of peanut butter, and you can spread this peanut butter in some way across the bread. And maybe it's wheat bread, right? I'll just draw some little specks. There we go. And so when you spread it, each distribution talks about how you spread it differently. For the exponential distribution, it spreads it really thick in the beginning, and then it kind of thins out over time. And that's generally what an exponential distribution looks like. That's supposed to be peanut butter. And so because a real valued number is uncountably infinite and time is real valued, you can't really talk about the probability of a single value, right? And so if you talked about time, if you said, what's the probability of something arriving after 1.53762 seconds, right? Because there are so many different real valued numbers, it broke our framework of probabilities. And so the only thing you can do is you can talk about how much of this 1 unit of peanut butter is spread over all the places you can spread the peanut butter, and then how thickly spread it is at any one given moment. That thickness is the so-called probability density function, and that amount of the unit spread across some span of your so-called support set or your run of bread from minus infinity to plus infinity, that's called your cumulative distribution function, or CDF. And the reason for that is because you can't talk about the probability of a single element. Does that make sense? Okay, to jar your memory from last time. And so this particular type of peanut butter spread is the exponential spread, and this exponential spread is not defined from 0 to minus infinity. It's only defined greater than 0 because time is only greater than 0. Does that make sense? So if you were to talk about integrating the PDF of the exponential distribution from minus infinity to plus infinity, our density function, f of x dx, and so that's the definition of the CDF, which is often written as capital F of x. And so how you calculate this is you do it by parts. You say, I'm going to take that portion from minus infinity to 0, f of x dx, and I'm going to add that to my cumulative spread, that CDF, from 0 to positive infinity, f of x dx. And of course, it's 0 everywhere it's undefined, so that term goes to 0. Does that make sense? But when you compute the CDF, you really start from negative infinity and go to positive infinity. And what you're using is the integral, which is a limit of the so-called Riemannian sum. And what that corresponds to, if you have a thickness function for your peanut butter that some function f of x, if you want to calculate all of the value for this f of x, the area under the curve, what the Riemannian sum says is I'm going to take these tiny sliver rectangles and I'm going to add them up. Why? Because I know the area of a rectangle. The height of the rectangle, that's just the value f of x, because I know how tall that is. I can evaluate that. The width, I'm just calling delta x. And if I let delta x get really, really, really small and add up these rectangles, that'll give me the area under this curve, or the total amount of peanut butter out of that one unit that I add up over all those places on the bread that it's spread. Does that make sense? Any questions? No? All right. So when we look at the summary statistics, the mean is 1 upon lambda, where lambda is the parameter, and that's a rate associated with the exponential distribution. And the variance is 1 upon lambda squared. And I've posted on the Canvas site some derivation if you're interested in the derivation. But I won't hold you for the hold you responsible for the derivation in this class. That's stochastic computing. Shameless plug, coming to you fall 2023. Okay, so let's look at the gamma distribution. We talked about the exponential and the exponential traffics in time, and there are some types of systems where the stochasticity traffics in time, but this time is structured as a series of steps that each takes time. If you take, for example, how you purchase something on Amazon, Target, or whatever, you visit the page, www.target.com. That takes some time. That's an exponential. You enter in a query. I'd like an Xbox. If you can find an Xbox System X, tell me where you can find one, because you can't find them these days. That's great. Before my daughter was born, I used to do gaming a lot, and I haven't done it for 11 years. Now she's ready to start playing games. But that being the case, my avatar is going to come back and wreak havoc on the online world. But anyways, so you enter a search query for your Xbox, and you hit enter, and that takes some time, right? So you compute a result set, that request. It's a client-server architecture. It goes to the server, it looks it up in the database, and it computes a result set from that database. It grabs those things that match the text Xbox from this large database on the file system. That takes time. That's an exponential. And then you see this result set. You see, maybe the, 500 megabyte version, the terabyte version that you can never find. That takes time, okay? And then you browse through it. You click on one of these items from the result set displayed by your browser, returned back by the server. That takes time. So then you add it to your shopping cart and you go ahead and you pay for it. That takes time. So each one of these steps takes time, and time is described by an exponential distribution, okay? And so this type of stochasticity is called algorithmic execution. It's a bunch of steps, and each of these steps takes some time. So it's a sequence of exponential distributions. But when we talk about this system, we talk about the total time, but the structure is different. It's a bunch of steps. And the reason why you have these steps instead of just one period of time, when do I reach the end, is because there can be some variability for each one of these steps. So you have to represent them separately. So it's a little bit different from just saying, I start at step 1 and I'm looking for the time for step 5 to complete, because it won't work well for you if you don't model each of the pieces. Okay, and so this algorithmic execution, each step we define as an exponential distribution, and it's governed by a parameter lambda. It's the same lambda when we talk about this algorithmic execution. And we're going to give a label, a name to the number of steps. We're going to say alpha many steps. Each step is independent. Absolutely, yes. Once you get the result set, you're clicking on something. But the time it takes you to look through the results and read the product reviews and then click on something, that has no bearing on the time it took to display the result set. It just happens to come after. And so each step is independent. And this algorithmic execution model is so-called, sometimes in the literature, a multi-staged execution. This is well defined by the gamma distribution. And I remember when I first saw that, I'm like, what the hell is that, right? Gamma. So the gamma distribution has two parameters, the shape and the scale parameter. Alpha is the number of steps in this algorithmic execution, and lambda is that time parameter, that rate parameter that governs the underlying exponential. Does that make sense? Any questions? No? All right. And so if you were trying to model performance of some web server, you would model that as a gamma distribution and then sample from it based on measurements, and then go ahead and do your simulation. And then you might use that to decide how many instances of your machine you'd have in the data center in order to guarantee a certain level of service so customers aren't waiting in their browser. This is the density function of the gamma distribution, and it gets its name, gamma distribution, from this leading coefficient, which involves something called the gamma function. And so here we have rate lambda to the alpha power, and then here we have gamma of, that should be alpha and not a. So alpha, this gamma function, is nothing more, if I have an integer, gamma of some integer a is just a minus 1 factorial. Why didn't they say that? That's a great question. You have to read through the history. I don't know why they do the things they do. But that being the case, this is our leading coefficient, and this distribution gets its name from this gamma function. And then we have x, the time that you're trying to compute the probability density for, x to the alpha minus 1, e to the minus lambda x. Now this, whoa, wait a minute, this looks familiar. This kind of looks like the exponential. Yeah, it does come from the exponential. And there's a relationship between the gamma and exponential. It's just some number of copies of an exponential. Does that make sense? All right. So I won't do any derivations, but the CDF, which is important to know for every distribution, is gamma of alpha upon lambda to the alpha power. And then if we look at the summary statistics, we'll end with this. We have about 1 minute left. The variance, the expectation rather, the mean, population mean, is alpha upon lambda, right? And remember, the expectation for an exponential is 1 upon lambda. We have alpha many of them. Oh, wait a minute. Alpha over lambda. That's 1 upon lambda added to itself alpha many times. And then the variance is alpha upon lambda squared. That looks very familiar. The variance of an exponential distribution is 1 upon lambda squared. We have alpha many of them, so it's alpha upon lambda squared. Does that make sense? And so if it's not in the assignment, because this is continuous, if you are computing the population variance and population mean, you would calculate it from the parameters alpha and lambda that you gave it, and then you'd sample, and then you'd show how what you calculate from the sample coincides with the population mean, alpha upon lambda, and the population variance. And you see that as the sample size increases, it gets closer and closer and closer and closer and closer. Okay, does that make sense? All right, any questions? No? All right, so we will end there, and we will pick back up on Monday with the normal distribution, which is a really important construct among probability distributions. All right, so we'll end there. Have a great weekend, and I'll see you all on Monday. Please take a look at Project 5, or at least run the Jupyter Notebook. Give yourself a head start. So I'll see you then.